Thank you. Thank you. Okay, this is not my slide. Peter Bonks is one of the preeminent database researchers on the planet. He basically sort of gave the modern shared nothing column store its form. And this is him being somewhat critical of graph database systems. I'm a graph database implementer, so a little bit nervous making. This is a great talk if you're a database person. However, it's quite technical, so I thought I would unpack it a little bit for you guys. So how many people out here have teenage children? Just show of hands. Yeah, okay. You guys are doing great. You're gonna get through this. Okay, you're my target demographic here. A graph database is like teenage sex. They're all talking about it. Some of them are doing it, and the ones who are doing it are not doing a very good job. So I'm here today as your own graph database teenager. It's like, whoa, you guys are home early. The lamp broke. And I guess we're going to have a talk. Okay, I'm going to talk about Liquid. Liquid is a relational graph database that we built at LinkedIn. Runs about 2 million QPS. It's a pretty standard, large-scale Silicon Valley database system. Now, as is usual with these things, I didn't build this by myself. I have a wonderful and talented team of probably 40 people now who make this thing a reality, but I'm shamelessly going to claim credit for their work. Okay, so first question is, why did LinkedIn build a graph database, right? Now the recruiter who brought me to LinkedIn explained LinkedIn to me. He said, look, the magic of LinkedIn is in the second degree. Like your first degree, all your connections, you already know who they are. Like you have your Rolodex and your email. It's not very valuable. But your second degree is all of the connections that you could have, but maybe don't yet, right? So like maybe your next job is in your first degree, maybe you'll go work with a friend, but probably your next job is in your second degree, right? Okay, so what we're doing fundamentally when we're looking at LinkedIn is we're browsing a large graph and we're figuring out what about that graph is interesting to us. And here's some of the stuff that comes out of the graph database. You notice these are all second degree connections. So what about a graph is interesting to me? Well, it's some sort of second degree connection. Like maybe we worked at the same employer, maybe we went to the same school, maybe we know some of the same people, right? Okay, so this is just one of 3 graph workloads. What we're doing is graph serving, and database people would call this complex OLTP. But what we're doing is we're browsing a graph. This is the predominant application workload. Even things like PowerPoint or Word, what they're doing is they're browsing a graph of stuff almost all the time. You do a little bit of editing, right? The important thing about serving is we need to work in human real time, right? Like about 1/4 of a second. Let it be half a second, but it's got to be like that fast. Now, you can also do graph analytics. Database people would just say complex OLAP or maybe just OLAP, where like you have an analyst typing in a query and they're happy to wait for a few minutes, or maybe they're running a dashboard, and it runs once an hour and prints comes up with a graph for somebody to look at. So there we're looking at something that scans a whole bunch of the graph and summarizes it and it's going to take minutes probably. And then there's a third workload, which is graph computation, things like PageRank, Bellman-Ford, where I want to run an algorithm over the whole graph. And these things typically take minutes or even hours, depending on the size of the graph and the algorithm. So, what we're doing is just graph serving. Okay, handy rule of thumb in software development: never invent something that's in a textbook. All of the background for this talk and this product is basically textbook computer science, literally, specifically the relational model and Datalog. This is actually the real textbook that we use as a reference on the team. You can see it's been thumbed through. Okay, so let's jump right in. Relational graph data, I'm going to throw some SQL at you. I'll speak it slowly. Basically, relational graph data is two tables, right? I have a table of vertices, and this is just mapping strings to integers. That's all it's doing. So a vertex is represented by a string. Inside the database, we'd like to represent it with a fixed length integer. That's what this does. Okay, now the exciting part, I have a table of edges. Well, an edge is just 3 vertices, right? And this is a compound primary key. So the edge, you specify it by value, and it either exists or it doesn't exist, right? It's very simple. Okay, pause right here. This is like 90% of the content of this talk right here. It just so happens, like a lot of things in software, that the remaining 10% of the talk will take the other 90% of the time. Okay, so let's look at some graph data, right? What we're talking about is basically just 3 columns of integers like this. And I've shown these guys, if this was a normal SQL database, they would be sorted like this because of the primary key constraint. Okay? So let's think a bit about what it's going to be like to work with this. So, like, suppose you start with a bunch of things and you want to transform them. You want to navigate through an edge. One edge for each thing, or multiple edges for each thing. Okay, you notice the things are all sorted, and the subjects are all sorted, so this is great. We do a merge join, and what we get in the output is no longer sorted. It's not even a set. So if we were doing like a complex query where we do multiple hops, through a path, right? We would have to resort this thing in order to keep on going, or do random access. Well, there's another aspect to this. Like, this is really small, but any kind of real database, the edge does not contain a lot of information, so you're going to have a lot of edges, a lot. Think 1 trillion edges, right? And I said our workload is browsing, right? So I have to produce a screen full of data for someone to look at, and I have to do this in about 1/4 of a second. So what I can tell you then is, if I only have 1/4 of a second and I'm looking at 1 trillion things, I can't actually scan very many things, right? Like, maybe I can scan a few 100,000, maybe 1 million things, 1 million edges. But it's, we're very limited in the amount of data that we can have as an intermediate result, just by the nature of the domain, right? So now think about it, like, so I have an intermediate result, it's just going to be a bunch of edges, everything is edges. So I have some intermediate result, it's got like 100,000 things in it, but I'm doing a lookup into a table of 1 trillion things, right? So it's just incredibly improbable that a page that I read for one thing would contain the answer for the next thing, right? So just by the law of large numbers, what you're doing when you work with graph data is random access, right? And so the key insight here is we're doing random access at scale. There's absolutely no way around this. So what we're doing, the index structures that we're using are hash tables, and the performance domain that we're working in, we're going to be counting L3 cache misses, right? Because we're doing random access into memory. So the entire graph is held in hash tables in memory. And that's, just keep that in your head as we go along. Okay. Before we get too much further, here's a question like, why only 3 things? Why not 2? Why not 4? Seems like kind of an arbitrary choice. The first reason, it's tractable to index everything. Like 3 factorial is 6. 6x is a reasonable right amplification if you're careful. So we can just index everything and say, look, edges are fast. There's no create index. They're just uniformly fast. They deliver random access. That's a guarantee that we can make. That's super handy. Second of all, like as subject predicate object would kind of lead you to believe, this is how people encode knowledge, right? So we are building database machinery that deals with knowledge the way people like to encode it, which seems like it ought to be a good idea. And there's a subset of people, computer programmers, and they like to use structs and pointers when they're building a model of the world in an application. So because the whole point of having a database is to build applications with it, right? So let's go look at that world a little bit. Okay, so you have a triple, like Herman Melville wrote Moby Dick, just a fact, right? And if you're an application programmer, you're probably going to model this as like, well, I have a struct author, and here's the one for Herman Melville. He wrote a book. He could have written many books, so there's a vector right there. And then one of the books that he wrote is Moby Dick, right? And similarly, okay, the Moby Dick structure, it's a book. Books were written by an author, and there's the author. So when you're programming with structs and pointers, what you're really doing is you're working with a hand-built inverted index of the underlying relation, right? Okay, so, well, some good news, right? Like, this is just a relational database. We can do this with SQL. Now, I'll pause for a few minutes while you guys digest all of this. No, I'm not going to. Yes?
Your last statement you said about when you're working with the structs and pointers, you're working with hand-built indexes?
Hand-built inverted indexes. Right. Okay. Okay, I've tortured you with SQL enough. We have a much better syntax. Interestingly, it's been sitting there in a textbook for 30 years. It's Datalog. This Datalog that you see on the screen is the same query that the SQL was doing. You see it has a natural decomposition into rules. And it's just sort of a basic social graph type of a thing. I'm looking for employers and skills of friends, employers and skills in my second degree. So these are rules. These are Datalog rules. I'm not gonna teach you all of Datalog, but I'm gonna teach you enough that you won't panic if I show you some later on. So in Datalog, anything with a period is a statement of fact, and in our Datalog, the only thing you can assert is an edge. At the bottom, everything is assertions of edges. So here I'm saying, user one, their name is Scott. Pretty straightforward. Anything with a question mark is a query. Underbar is a variable, which just means, I'm different from all other variables. Every underbar is different. So all you're doing here is you're asking, what is the name of user one, right? Pretty simple. And I can define a rule, like here's a rule called named, and the rule just evaluates the right-hand side, I guess. Same sort of thing. I can ask who has this name, or what is the name of this thing, just by supplying different variable bindings. A cool thing that you can do with Datalog and edges is you can say, well, user one, like, what's up with that? Like all the inbound edges on user one. This is a very, very typical first step when you're exploring a new database with a schema that you're not familiar with, right? You find something that you know, typically yourself, and then you go explore just by looking at the inbound edges. And it's something that's very difficult to do in SQL. Okay. So our two-table representation actually lost some valuable information. And we need to add this information back. And we're going to do this by formally defining predicates. So here's a rule called defpred, and you have to use defpred to introduce a predicate. So this is a predicate for title, like the title of a book. And what the definition says is, hey, the subject side, a book only has one title, so it's cardinality 1. The type of a book, well, it's just a node. And on the object side, there's a string, a UTF-8 string, so our type is a string. And of course, many books can have the same title, right? So 0 meaning unlimited cardinality, right? So all you have to do to start using a new kind of predicate is put this defpred in, and then you can immediately start using it. So for example, book 1 title is Moby Dick. Now the predicate itself is just a node in the graph like any other node. So you can add your own metadata to predicates, right? So for example, here I'm saying, well, there's a kind of a predicate that's like a name-like thing, right? Like a title is like a name is like a name. And so I'm gonna identify these as being of type known as, right? Just writing edges in. And now I can ask queries like this, right? So what we're saying is, well, there's a thing, U1, I don't know much else about it. It's referred to by an edge with some kind of a predicate. And the kind of predicate is anything referred to by an edge with the type known as, right? So I'm able to define what it is, what a name-like thing is, and I'm able to ask for it in a query. And if you look at like what an application does, very often this is exactly what they need, right? Like I have a little card, it has a name, it has a picture, and so forth. I use this to display anything. I don't care. As long as it has a name and a picture and maybe some descriptive text, right? Okay, so that's predicates. Now, we're not quite done yet, because the predicate is a simple binary relationship, right? But most relationships in the real world are not simple binary relationships. Let me give you some examples. Okay, grammar is more than subject, predicate, and object, right? And here's some real relationships that are not subject, predicate, and object. You work for a company. That's employer, employee, and a start date, right? If I don't add the start date, then I can't represent a common situation in the world where you work for a company, and then you quit and you go work for another company, and then you quit and you go back and work for the first company. And that's actually a super important piece of data, right? Like LinkedIn calls this a boomerang, right? Similarly, a marriage, spouse, start date, right? You have people like Elizabeth Taylor who are married a lot, sometimes to the same people. Again, if you want to model the data, you need more than a binary relationship. Another one, actor, role, and film, endorser, endorsee skill. N-ary relationships happen all over the place. And we need support for these guys in a graph database. And like one more thing, a lot of relationships have attributes that describe them that are not part of the identity. Like a super common one in our world is a score. Like, okay, this relationship exists, but how important is it? Like Herman Melville wrote a book, but what's his most important book? Which one should you show first? Other things might be like a stop date, or maybe a title, something like that. Okay. Well, the basic intuition here is like, if I have an edge and my edge traversal is fast, then it's not really objectionable just to add an extra hop, right? Like, if going across one edge is going to cost you like 2 L3 cache misses, okay, going across 2 is going to cost you 4. I mean, that's not outrageous. Kind of like honestly represents the structure here. So, your big question is, well, what do I use for the identity of this central node, right? Like, if I just make one up, well, now this N-ary relationship doesn't behave like an edge, right? Like you can get duplicates, right? And if you have duplicates, then you might add interesting data to the wrong one. It's not really an effective way to work. Okay, but we can actually solve this problem, and we're just going to have a function which generates us a string, which is the identity of this central node. And you can kind of read the string and get how this works. Like, I'm going to take all pairs of object and predicate, and I'm going to sort them. And that's the identity of this hub node, right? And once we figure out that, the way edges work, now N-ary relationships work just like edges, right? So we kind of get this for free. And you can annotate. You can do anything you want with a central node. It's just a node. It's not going to bite anybody. So you can put whatever data you want on there. And the data is just edges. We don't need to come up with some sort of fancy schema to talk about this stuff. Okay, so Liquid does this with what we call compound predicates, and this is just the syntax of that working. Okay, well, what is this thing that we built? This has been known to relational database types for a long time. I think in like the 70s, Peter Chen came up with this notion of entity relationship modeling. And this thing that we've come up with is just a relationship table, right? It says, well, there's a compound primary key of actor, role, and film. And then you have some attribute columns, whatever you want. So this thing that we invented is actually completely normal, well understood 40-year-old SQL. There's a nice bonus that you get out of this, right? Suppose we wanted to do a symmetric relationship, like a mutual friend, right? Well, you'd start off in SQL, it's like, okay, yeah, I have 2 friends, like friend 1 and friend 2. And okay, so now I have Bob and Jane, they're mutual friends. Well, I mean, is it Bob and Jane or is it Jane and Bob, right? There are 2 different ways to represent that. So pretty quickly, you're going to reach for your PL/SQL hammer, and you're going to say, okay, well, friend 1 has got to be less than friend 2. That's the way we know, the identity of the mutual friendship, right? Okay, but if we're in this N-ary relationship world, what I'd observe is like, well, if you just had two friend edges, it's in fact structurally perfectly symmetrical, right? The structure expresses exactly what we want to express. Furthermore, our little algorithm for generating the primary key works exactly right? We sorted the predicates are the same, Bob sorts ahead of Jane, so now we have a primary key. So that's pretty cool, right? Like this is actually something SQL can't do. And here's a little bit of Datalog, and I'm showing you I'm asserting the edge twice in both different orders, and then at the end I ask for the inbound edge as a Bob, and you can see there's only one inbound edge, right? So there's just the unique mutual friendship. Okay, so now a question you might ask here is like, well, what about nodes? Like, we've only talked about edges. That's kind of on purpose. Nodes are just immutable strings, like their primary keys. They represent entities, that's it. Okay, sometimes they parse. Like you could have a node that's like 7. 7 has a meaning as like an integer. And so when we give that node a type, like int, it just means I want something that parses as an integer. So a question is like, well, why not more? Like, why don't we put a bunch more stuff inside our node? And I mean, if you have something that has like node properties, like a question to ask is like, why even have edges, right? Like, I can have a node be like an author and another node be like a book, and the book would have like a little vector of author identities in there. I mean, why not just do stuff like that? Okay, we tried this back in the 90s. I was involved with this. ODBs, they don't work very well. So in this world, say we have a person, right? That's a base class. People have a name or something like that. And then we have a person who's an author, right? That's a subclass. We're just working on structure extension here, subclassing. That, like, okay, no one could object to that, right? Okay, well, what if I have a person who's an editor? I can solve it the same way. Okay, what if I have a person who's an editor and an author? Well, now I have kind of a problem, because either I figure out some sort of multiple inheritance thing, which never worked very well, or I have two different identities, two different structs, one for person as an author and one for person as an editor. And now equality doesn't work the way you think it ought to work, right? But it gets worse. Like, you're making an assumption here, an ontological assumption that all authors are people. And that's not actually the case. So back in my history, starting with graph databases, worked at MetaWeb, kept discovering that the Beatles, a rock group, were getting typed as a person, right? Well, it turns out that we were trying to do an inheritance-based type system. We said, well, an author, that's a subclass of a person. And it turns out the Beatles authored a book. Like, there are books in the world, and they have a title and a name, and the author's name says the Beatles. It's a fact. I'm not making this up. This is Amazon right now, right? So the notion that you're going to have a single ontology that is going to support everything is really, really badly broken. There's another interesting problem with it, which is like the root of your hierarchy becomes a gigantic single point of failure, right? Like, you do some clever editing up at the root, and suddenly 2/3 of your database just disappears, right? The nice thing about a graph, about the graph structure, is it doesn't care. Like, we're just recording facts. The triples don't need to have a particular order of structure fields. They just exist. They don't do anybody any harm. So authors, editors, astronauts, all can cluster around the same identity without any conflict at all. Okay, so that's sort of the data model. I want to talk a little bit about query evaluation, just a couple details. The first problem is cross products, and the second problem is static planning, and these are both kind of endemic to SQL. Okay, worst case optimal joins, super interesting, big giant topic. You can go search for that on Google Scholar or something and read about it. It's very relevant to a social graph kind of a workload, but it would be a whole nother talk. Okay, so let's look at a cross product. So I'm going to use a predicate like knows, you know, A knows B, B knows A. So there's an edge. Okay, now I'm going to define a rule that's bidirectional, right? So I just ask, you know, knows X, Y is either X knows Y or Y knows X, right? And now I'm going to say, show me, you know, who knows who in the whole database. And I get two results, right? A knows B and B knows A. The simplest cross product that I could come up with. Okay, but if I look at the edges, there's this one edge, right? Okay, why is this a big deal? Well, we're doing complex queries. We're doing complex queries of many-to-many relationships. Every time you introduce a cross product, you're multiplying the size of your results by some constant factor, 2, 3, 5, 10, something like that. So it's really, really easy to get results that are 100 times the size of the actual edges, right? If you're doing a complex query. And why do we care? Well, inside a database, we do lots of clever stuff to avoid materializing cross products because it's really hard. If you have n times m things, you wind up doing n times m work, and that turns out to be slow, right? And you know, a key point here is like the application has exactly the same problem. They don't want to do n times m work either. Okay, so how does this play out? What we need is a subgraph return. So typically in SQL, SQL only returns you a single table, right? So a subgraph return, I just want to return multiple tables, right? So you can think of this as I want to return one row in every relationship table that matched, right? And I can stitch this stuff together as it's a relational algebra tree, like what we have inside a SQL engine. And really, I only need two things in the tree. I need cross products, and I need outer joins, right? So like if you're processing this data as an application developer, you're building up a graph of people and skills and employers. So you know, you're going to have some sort of a loop where you say, oh yeah, person 23, do I have one for that? No, okay, I'm going to make one. Okay, skill 7, do I have one for those? Okay, and I'm going to create one. Now, you know, the struct for 23 is going to point at the struct for 7 in the correct offset. Okay, that thing that you're doing with the hash table lookup to see if you have one, that's an outer join. That's all it is, right? It's nothing mysterious. Okay, dynamic planning. Let's look at a really simple query. This is graph distances 3. It's very relevant to our workload. And it's just 3 hops, right? You know, A is connected to B is connected to C. That's all it is. So I want to, you know, the workload is actually, I want to know if Alice is 3 hops from Bob, right? Okay, there are only 4 possible plans in a sequential world, right? I can go left, left, left from Alice. I can go left, left, right. I can go left, right, right, or I can go right, 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 right? The only ways you can do this query. None of these plans are optimal for all data, right? And we're doing self-joins, so all of our statistics, to our statistics, each edge constraint in this query looks identical. They're all the same, right? But what makes them different is like what data is in the graph. Now, an observation here is, unlike in a sorted storage world, in a hash table storage world, our set sizes are available in constant time. Like I can do a hash lookup and I can know how big the set that I'm going to read is. If I'm storing stuff in a B tree, like I B search to find the beginning of it, and then I have to B search to find the end, right? Or I can just scan it. But it's far more expensive to find out how big a set is. Okay, so what does this look like? We just hand-coded the 4 plans. You can see them on the chart there. And you can see like there's this kind of scallopy thing with 4 scallops. That's where each plan is optimal, right? Now the dynamic plan, you can see it's not quite as good as perfectly optimal because it costs you a little bit to figure out how to use it, right? Like we're going to say, okay, how big is the fan out from Bob? How big is the fan out from Alice? Okay, pick the smaller one, expand that. Did that get super huge, right? So we have to do some work to figure things out. But we can do that work. It's tractable to do that work in this indexing domain, and you get a query evaluation performance that is pretty close to optimal in all 4 domains, right? Okay, so I'm kind of winding up. What I want to do, what I want to leave you with is a formal definition for what a graph database is. This is not as racy as the intro. Okay, graph database is an implementation of the relational model with 4 properties. Okay, all relationships are equal. Everything is an edge. If you think about like a typical SQL database, if you're a relationship that is in one table, you're first class, right? It's super nice. Like I do a B search, I get the row, and I have this whole relationship right there, you know, basically for free. But if you're a relationship that exists across tables, like I have to do a join, you're really second class. Joining is super slow, so second class that way. And semantically, SQL doesn't really keep track of what joins were intended by the user, right? SQL will happily say, yeah, you're joining depth in fathoms to degrees Celsius. You know, probably okay. So in the graph database, everything is an edge, and the edge is exactly what the user intended. Those are the joins that the user intended. If everything is going to be an edge, you're going to have a lot of edges. It better be fast, right? If it's not constant time and fast, and by that I mean like 3 L3 cache misses, well, as your database gets bigger, your performance gets slower. Ultimately, it's not going to be worthwhile having a big graph. You want a smaller graph that performs better, right? That turns into harder to manage. Okay. Query results are a subgraph. If I'm going to have a big graph with a lot of edges, I want to ask complex queries of it. I need to return structured results that the application actually wants to consume. And lastly, schema change is constant time. if you think of it like a general model for a serving system, it's a materialized view, right? Like I did some fancy query, and then I just want to save it, and then when you ask something, I just look up a row and give it back to you. So what we're saying with this is, no, you can't cheat. I need to be able to show up with a new kind of predicate and just start using it at full speed. This can't turn into any kind of like alter, table, fire drill underneath the surface in the implementation. Okay, that's it. That's my proposed definition for a graph database. Clearly, I disagree with a lot of the world, so we'll see how that turns out. So I want to do some, just a brief comparison walkthrough. So first of all, versus SQL, well, there's no denormalization. A graph is perfectly normalized. It is in fifth normal form, and you can't express denormalization. There are no nulls or trinary logic. Like, edges either exist or they don't. And if you introduce an unbound variable, we're going to force you to give it a binding. So if you have like a default quantity, you get to decide, is it 0, is it min-int, is it max-int, is it 1? Depends, which is appropriate, depends on what you're doing with it. But we force you to make that decision explicitly. So now there's no trinary logic, right? Which is a big pain. We can do constrain through the predicate. So in SQL, a predicate is typically a column, roughly. Well, you're welcome to use the catalog table, but it's hard to use the catalog table meaningfully in a query. So typically, to do something like this in SQL, you need to like query the catalog, figure it out, and then you generate another SQL query. Remember, so constraining through the predicate is like, this predicate is a name-like thing, right? You can explore all the incident edges on any entity. So, you have a ticker symbol, Microsoft, that's in the graph somewhere. You can go start exploring. You can do symmetric relationships, and you have subgraph results. Okay, RDF. Okay, the relational model. That's pretty cool. It's been 40 years. We've had 20 years of NoSQL. There really isn't much of a contender, right? We did not invent a query language. I highly recommend that. We have a much simpler edge. We have first-class schema that is much simpler than OWL. Like you've seen all the moving pieces in the schema in this talk. We can do N-ary relationships, and we can do symmetric relationships, and we have composable rules. And lastly, versus property graphs, relational model, didn't invent a query language. We have a first-class schema for everything. You can constrain through the predicate. There's no separate property schema, right? Everything is just edges. There's no OO node problems. So we just make the decision for you. You can't put any stuff in a node, just use edges. N-ary relationships, again, super common. Composable rules. Okay, so what's the future here? A lot of people think that the future of data is big graphs. Okay, if the future of data is big graphs, then I think the future of applications is big queries, right? You ought to be able to say, hey, here's all the data that I want to put on a page. Here's a description of it. Go get it for me. Even if I need to do this, I'm doing thousands of joins in real time, human real time. Okay, so I hope that this encourages you to, or gives you tools to make good choices in the world, and I'm ready to take questions.
Thank you for the presentation. My question is, how do you add, in LinkedIn, I believe there is a feature where there's a representation like.
Sorry, could you repeat that?
So there is a feature in LinkedIn, I believe, where you can have a representation like I am 80% good in Java and weaker in JavaScript or something like that. So how do you add that weight in these edges?
Oh, yeah, you would have a compound relationship with a skill, so you have that hop in the middle, and then you just add a score edge, whatever you want, a floating point or an integer score. Yeah.
Thank you. Any other questions?
I have one. Do you put any limits on fan out, either on the query engine part or in the representation?
There are no limits on the fan out. If you have a, naturally in a social graph, you're going to experience skew, right? So like, I don't have very many followers, a few hundred. Bill Gates has 20 million followers, right? That's not a normal distribution. It would be a zip distribution. That's kind of a benefit of the graph representation, is you can represent stuff like that. No, the implication is your query eval better be able to deal with skew, right? Like if you have a bunch of people and you're looking at the fan out from followers, it might be 200, 700, 900, 200, 20 million. Well, when you get to 20 million, probably time for a different query plan.
I would like to understand what use cases would you recommend to use graph database? Like we may have different options or approaches there, like GraphQL or big data, which also help us to search faster with Python of the data joins. And each may have its pros and cons. Like for graph database specifically, we are looking for fitting use cases that this could be the optimal approach to SQL.
Okay. What are the use cases? What are the pros and cons? So for the data model itself, for how to model data, I don't think there are pros and cons. I think the graph is just better. And it's isomorphic to entity relationships. So if you wanted to do normalized entity relationship data modeling in SQL, that's great. It turns right into a graph. For querying, obviously, it really just depends on the workload. The observation I'd make is serving is kind of a new workload. Like people typically handle this with cache in front of a conventional database, right? And really the difference between a cache and an index is just the index is complete and it has some consistency properties that you can state. Whereas, the cache is just whatever the application put in there. Like if you have an object relational mapper, it's running a cache of objects. I think that's pretty undesirable. I think indexing is much better. There's no warm-up time. You know how much things are going to cost, and it's immediately usable at full speed. So the previous system at LinkedIn was a cached system. The current system, Liquid, is uncached, right? And the SREs love that. They